three-dimensional vectors. So what is a vector in a three-dimensional space? Well, it's just an ordered triple of real numbers. So instead of having AB, we now have ABC. It's natural extension, right? And for vectors U, where you write it as U1, U2, U3, and V equals V1, V2, V3, and the scalar C, we have the corresponding definitions here. So the length is almost like before. We just add this third component. You might wonder why this is still like this. I mean, why is it not cubed? U1 cubed plus U2 cubed plus U3 cubed, and then the third root, not the second root of this number. I can illustrate this afterwards on the blackboard, but it turns out to be the natural extension. This is the length of U. If you add U and V, you just do as before, only you have a third component. Scalar multiplication is the same as before, only you have a third component. This identity still holds. If you take the length of C times U, it's just the length of C times the length of U. Again, you have the 2 points determine a vector, so you have a point P consisting of these three coordinates, and that point Q consisting of these three components. Then, as before, the formula for the vector from Q to P is just P minus Q, and the length is just like this, as before. So everything translates nicely. Today we will not discuss why there are additional structure in 3 dimensions that you don't have in basically any other dimension. One could argue that you also have this structure in 0 dimension and 7th dimension, something like that, but it's not important. There's some extra structure in 3 dimensions, but for now everything just translates nicely, right? So you have this, you have this point here, and a vector ABC is just you go out A along the x-axis, B along the y-axis, and C along the z-axis, right? And then you end up here, and then you have an arrow here. Since we now have an extra dimension, we also have an extra standard basis vector. So following the alphabet, we come to K, and this is now, I is now not 0, 1, but 0, 1, 0. J is 0, 1, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. The obvious definitions. So I have illustrated them down here. So here you have an I vector, a j vector, and a k vector. So they just point in the direction of positive x-axis, positive y-axis, positive z-axis. And as before, you can split up any vector into a sum and scalar. So I will use a word now that we'll get back to later on. If we have a number of vectors and a number of scalars, and we multiply each scalar onto each to a corresponding vector, and then you add everything up, the result will be called a scalar, a linear combination. So a linear combination is something of this form, and it turns out that linear combinations are very handy in many ways, because you can use this scalar, this linear structure that I mentioned that linear transformations should respect to do all kinds of nice things. So this is important for reasons that are not completely obvious at the moment, at least if you haven't seen something like this before. But it turns out to be nice to be able to split everything up.